Namaste everyone. Welcome back to the waves first PUC CET NEET classes. Now today we will discuss about stationary waves. What are stationary waves? When two sound waves traveling in the same direction superpose, we get beats of slightly different frequency. If they are in the opposite direction, if the two sound waves, identical waves of the same frequency, when they travel in the opposite direction, we get stationary waves. So for that, what we do is to get the identical waves, we make the same wave to get reflected back. So when two waves of similar kind, they travel in the opposite direction, when they superpose, we get stationary waves. What do you mean by stationary waves? All the particles vibrate, but they vibrate with a fixed amplitude, and they never change their amplitude, and the energy is not carried away from a particular place. It is restricted to a certain region. That's why it is called stationary. Whereas in a progressive wave, one by one particle will vibrate and a vibration will be transferred, energy is transferred, and it keeps on moving. But here it is restricted between two places: the origin, the source of sound, the source of a wave, and the reflected region. It is restricted within the region. That's why it's called stationary wave. Whenever a wave gets reflected from a surface, there is a 180-degree out of phase, one thing. And if it is a hard surface, if it is a soft surface, of course there may not be a 180-degree phase difference. So if you take a thread, we will explain what is a stationary wave first. If you take a thread like this and tie it at one end and go on vibrating it at the other end with different frequencies, number of times you vibrate per second, then the forward traveling wave will hit this and the reverse traveling wave will be reversed with the 180-degree out of phase. This is only a wave, the diagram of a graphical representation. Now when the forward traveling wave and reverse traveling wave travel through the same medium, particles are in a confusion now, whether they should listen to the forward traveling wave and vibrate, or they should listen to the reverse traveling wave and vibrate. Two waves are traveling simultaneously in a medium. That is what you call superposition. Whether the particles have to vibrate according to the first wave or second wave. So resultant vibration is produced. When the first wave and second wave superpose, particles will vibrate in the resultant amplitude or resultant displacement. How will be the resultant displacement? You will surprisingly find that at some places there is no vibration at all. Those particles are permanently at rest. Why is the reason? What is the reason behind it? The forward traveling wave will try to pull it up. Reverse traveling wave will try to pull it down. There is a 180-degree difference, phase difference between the two vibrations. What happens? The particle doesn't vibrate at all. At some places, particles vibrate with the highest amplitudes and they keep on vibrating with the same amplitude. They don't change their amplitude at all. At some places, the amplitudes will be in between 0 and maximum, and particles will continue to vibrate with the same amplitude. They never change it. So there are different particles with different amplitudes. Some particles don't vibrate, some particles always keep on vibrating with maximum amplitude, some particles vibrate with an amplitude which is 0 and maximum. So this repeats every now and then. And if you observe a loop, this is called a loop. This is called a loop. In a loop, particles will be vibrating like this. Suppose you take a string and make the string to vibrate. Say the vibrations are like this. Say, what do you mean by this? At this position, pressure is highest and density is more, and the particles don't vibrate at all. And that particle is called node. And the particles, the positions where particles vibrate with the highest amplitude is called antinode. And the distance between two nodes is called, or the region between two nodes is called a loop. And you can find that this is lambda, right? This is lambda, and this is lambda by 2, right? And the distance between two successive nodes or two successive antinodes, that is also true, is lambda by 2, half of the wavelength. And the distance between a node and a successive antinode, very next antinode, is lambda by 4, and this is called a loop. In a single loop, all the particles are vibrating in phase. What do you mean by that? You see, amplitude of this is 0. Amplitude of this is maximum, 2a here 0. Amplitude is equal to 0 here in this position. At the node, amplitude is 0. At the antinode, amplitude is 2a. What about the amplitude of other particles? This particle will be vibrating always with this much of amplitude, not with the highest. This will be with the highest. This will never be vibrating at all. So you don't see such particles in a progressive wave. In a progressive wave, all the particles get a chance of reaching to the amplitude one by one, but not simultaneously. They reach the amplitude one by one, but they will, when they get a chance, they reach to the highest amplitude, the same value as the previous one has reached. But here not like that. Some particles don't have the opportunity to vibrate at all. Some particles have the opportunity only this much. Some particles have this one. Now, inside a loop, you will surprisingly find that even though they have different amplitude, all of them go together. One particle goes to its highest position. Another particle goes to the highest position here. Another particle goes to its amplitude here. Amplitudes are different. Another particle remains there only. But they go together. In a loop, they come together down, go to the upper part. So in a loop, all particles are in phase. They may not be going to the highest position. The values of highest position defined the same for all the particles. That is different. The maximum amplitude, the maximum displacement is different for different particles, maybe, but they go to their maximum position simultaneously. All particles have same phase. All particles vibrate in the same phase in a loop. That means, imagine 10 students standing in a row, all of them throwing stones. And so imagine that the strength of different students are different. The one who has got maximum strength is standing in the center. One who is having less strength is standing at the edge. That they throw stones. Students at the edge are not throwing stones at all. The person in the middle is throwing it with the highest amplitude. So highest maximum amplitude. So the stones will move in this fashion, right? This stone will move here, this stone will move here, the middle one will move here. So once they reach their topmost position, the position of the stones will be like this. And all of them go to the top and come to the bottom together. The highest positions may be different. So they go like this, because every particle leaves the equilibrium position together but travel with different velocity. The one which travels with highest velocity goes to the top and comes back in the same time as the other one. So period of oscillation is same for all the particles. Very surprised. Even though this particle is vibrating only this much, this is vibrating only this much, their velocities are different. So that's why they complete the maximum amplitude and minimum amplitude in the same time. This may go to maximum amplitude and come back. This may go to small amplitude and come back. But they finish it in the same time. So all the particles leave the equilibrium position together, go to the maximum value, come back together. Phase is same. State of vibration is same. Period is same. Velocities are different. What about the neighboring one? If you consider a particle here and here on either side of a node, that means in different loop, very neighboring loop. When all the particles here go up, here particles come down. So when all the particles in one loop go up, another loop come down. Otherwise, the whole string will not be balanced. This is to have balancing of the whole system. And so what is the phase difference between the particles vibrating in the adjacent loop? 180 degree, not in phase. So particles of adjacent loop are 180 degree out of phase. When one goes up, another will be coming down. When this goes up, other will be coming down. So it is as if when you walk, how do you put your hands? Your hands will be 180 degree out of phase. When your one hand goes forward, your body bends back. In order to balance that, you will put another hand backward. So the whole system is in equilibrium. Body will be in equilibrium, but hands will be moving like this. They are 180 degree out of phase. You can't walk with both the hands forward and backward like this. It becomes difficult because body will not be balanced. So particles in the adjacent loop are 180 degree out of phase. Okay, that is the situation. And okay, now if you take such a stationary wave, it can be produced. And remember, stationary wave is a wave, it's a superposition of wave, and it is a superposition of any type of wave. It may be sound wave, it may be even longitudinal waves can superpose, and transverse waves can superpose. It may be a waves in a string, water ripples, it may be sound waves, anything. Now if you take a string, if stationary waves are produced, So make a string to vibrate, and if stationary waves are produced, how many loops are here now? One loop, 1, 2, 3, 4, 5. 5 loops will be produced when you vibrate it very fast. If you vibrate it slower, lesser frequency, it may vibrate with only, how many? I'll cut short. Okay. 1, 2, 3, 4. It may vibrate with 3 loops also. It may vibrate with the 2 loops. This depends on, it may vibrate with only 1 loop. It depends on how fast you vibrate, frequency. A wire can be made to vibrate in different frequencies. This is called the lowermost frequency, and this is called higher frequency. Any higher frequency is named by a term called overtone. Overtone is a higher frequency. This is more frequency. Suppose this is 5 Hertz, this should be 10 Hertz because there are 2 loops, and it is multiplied in integer form. 10 Hertz, this is 15, 20, 25, multiples of 5. If this is 3 Hertz, then this will be 6, and this will be 9, 12, like that, multiples of integers. So in a string we have all the frequencies of vibrations, all integral multiples of frequency of the fundamental mode. This is the lowest frequency with which you can make it to vibrate. When a string is made to vibrate, you should tie it at one end, correct? You must tie it at one end. At another end you have to hold it. That means string is bound here and there. And wherever it is tied, there should be a node. There is no chance. So the fixed ends must be a node. So you are holding it here in your hands and making it vibrate. So this is held here and just pluck it here. We will do it like that. Hold it here, pluck it. Then this should be a node, and these 2 ends should be a node. So in such a case, you will have the fundamental vibration like this, the least amount of frequency, and this is called fundamental frequency, F. Least frequency is called fundamental frequency. Next higher frequency, it is called first overtone. Which is the first overtone? 2F. If this is 5 Hertz, this will be 10 Hertz. Sir, this is 2 times the fundamental, so it is called second harmonic. Any higher frequency is called overtone. But if it is an exact multiple of the fundamental frequency, then it is called such and such a harmonic. How many times the fundamental? Sir, it is 7 times the fundamental, 7th harmonic. If it is 3 times the fundamental, 3rd harmonic. So this is first overtone, and this is also called second harmonic. Harmonic is another name for frequency, that is harmonic, overtone. These are all representation of frequencies. What about this one? This is 3 times the fundamental, so this is called second overtone, and this is 3rd harmonic, like this. So a wire can vibrate in all the harmonics. First harmonic, 1 times the fundamental. Second harmonic, 2nd time the fundamental. 3rd harmonic, 3rd times the fundamental. First overtone, second overtone, third overtone. Any higher frequencies are called overtones. A wire can be made to vibrate in any times the fundamental frequency. Fundamental frequency means it should vibrate in such a way that the 2 ends should be node, and in between you should have an antinode, because 2 ends are always tight. A string in a piano, string in a violin, string in a veena are all tied at the 2 ends. So if you pluck it, 2 ends must be node. So this is the basic way you can vibrate it. Okay. Now frequency of vibration of any stretched wire. You remember the experiment that you did in sonometer. It is like this. Here are the 2 bridges, and here is a wire, and it is under tension, and it is made to pass through a pulley here, and this is under tension, mg. Now these 2 ends will vibrate like this, or like this, many loops. Frequency of vibration of a stretched wire is 1 by 2L into square root of T by mu. What is mu? Mu is called mass per unit length. Mass per unit length of the wire, mu. And if mu is the mass per unit length, mu is mass of the wire by length of the wire, total mass of the wire by length of the wire. Now shall I add a n here? Why? Because if it is the second harmonic, Fundamental is first harmonic, 1 times the fundamental. Second one is second times the fundamental, second harmonic, 2 times the fundamental, and it is first overtone, right? So n equal to 2 you put. So like that. So this formula is very, very important. L is the length of the wire between the two bridges, or the point between the two extreme nodes, and n is number of loops also, because in second mode, second overtone, or in first harmonic, second harmonic and first overtone, there are 2 loops. So number of loops n, or higher frequency order harmonic, anything you can write. T is the tension, mg. T is tension, mu is mass per unit length, and number of loops, length of the wire. Now here one more formula you have to remember, that is suppose that wire is in the cylindrical form like this. If the wire is a cylindrical form, if you use a thicker wire and thinner wire, what is the difference? Here comes the difference. A thick wire of 1 meter weighs more, a thin wire of 1 meter weighs less. Then comes the difference in mass per unit length. Sir, can I change this mass per unit length now? Mu, mass per unit length. Mass of the wire can be written as density into volume per unit length. What is volume of this wire? This is pi r squared into L, correct? Into length. So shall I change this mass per unit length as density 4 by volume, isn't it? 4 by 3. No, not 4 by 3. It is not a sphere. Density into volume. Volume is pi r squared L by L, right? This L is in the formula itself. Mass per unit length. Volume is pi r squared L. L gets cancelled. Rho pi r squared. So shall I write a new formula for frequency of vibration? N by 2L. N is number of loops. If it is fundamental, n equal to 1. Root of tension, T equal to mg by mu. Mu is rho pi r squared. That means frequency is inversely proportional to thickness, radius, or diameter, whatever it is, this diameter. So frequency of vibration of a wire is inversely proportional to r, root of r square you have. You can take r outside. Frequency is directly proportional to root of tension. Frequency is inversely proportional to length of the wire. So it goes on. These factors are very important. So that is the formula. So right. So shall I write? Here root of n by 2L into root of n by 2L into root of T by rho pi r squared. That is also important. R squared, I put it in inside the square root, you can take it outside the square root. That is one thing about the stretched wire. A stretched wire vibrates in all the modes of vibration. Fundamental, first time the fundamental, first harmonic, second harmonic, third harmonic, everything. Now take an open pipe. A pipe open at both the ends. If you take a PVC pipe and blow air into that, it makes a sound like a shankar, right? That sound of boom sound you will get. And that sound, you can do it using a tuning fork also. Take a PVC pipe, strike a tuning fork and hold it at the mouth of this pipe. Then you will get a sound. Now, what is and suppose you have a pipe, say, as if you have a pipe in resonance column experiment. You do it in first year piece. Long back you did it, you might have forgotten. So that resonance column pipe, you take it. But don't dip it in water. Take it open like this, or both the ends open. You see, most of the musical instruments are open pipe. That saxophone, which is open at where you blow air, open at the other end, and flute, open at both the ends. Most of them are open pipes. If you take an open pipe, imagine you have a bundle of tuning forks. You have 1 Hertz tuning forks, 2 Hertz, 3 Hertz, 4 Hertz, 5 Hertz, 100 Hertz, 150 Hertz, 300 Hertz. You have a bag of tuning forks. Take 1 Hertz, hold it here. See whether you get maximum sound or not. No sir, throw it away. Take 2 Hertz, sound it here, and place it here. Let it produce sound here. So let it vibrate here like this. Sir, are you getting sound? No sir. 3 Hertz, 4 Hertz, 5 Hertz. Test it with different frequencies. Sir, I don't get sound for 30. 35, I hear a weak sound, sir. 40, I hear a maximum sound, sir. 45, very good sound, sir. 50 Hertz, very maximum sound, sir. 51 Hertz, no, lesser sound. 52, less. That means the sound increases to the maximum at 50 Hertz. Then it starts decreasing. If it is so, 50 Hertz is its fundamental frequency, because before 50 Hertz you don't get any maximum sound. After 50 Hertz you don't get maximum sound. and maximum sound is at 50 Hz. 50 Hz is called fundamental frequency. At this moment, how will be the stationary wave formation inside the pipe? It should be an antinode here, antinode here. Can you tell me why antinode? Both are free ends. Both the ends of the pipe are free ends. So it should be an antinode here and another antinode here, means you have to cut it here. You should have a node, right? If you take a wire and if and if two loops are produced, how do you create the situation of antinode and antinode? Antinode, antinode. That means you should get a node at the center. So a node at the center and two antinodes are formed. Antinode, node and antinode. What is this distance now? What is the length of the pipe? Length of the pipe is how much? Lambda by 4, lambda by 4. You know that a node to node, lambda by 2. Node to antinode, lambda by 4. So lambda by 4, lambda by 4. What is this one? 2 lambda by 4, correct? What is this one? Lambda by 2. Now what is the velocity of the sound now? Now lambda by 2 is equal to L. What is lambda is equal to 2L? What is the frequency of sound? F equal to V by lambda, because you know V is equal to F lambda. Frequency of sound here is F equal to V by lambda. V by lambda, 2L, right? 2L. This is the fundamental mode of vibration. F1 is equal to V by 2L. And what is the next mode of vibration? Sir, for 50 Hz I got the maximum sound, sir. This experiment is done quite opposite to the way in which you do the experiment in the lab. In the lab, what do? You don't fix the resonance column pipe height and try it with different frequencies. Why? Because purchasing 1 or 2 tuning forks in the lab per year itself is a difficult task. How can you purchase a bag of tuning forks? Instead, we go for a change. What? We will fix the tuning fork, we will change the length of the pipe. So either length of the pipe should be changed or tuning fork has to be changed. Easiest is changing the length of the pipe. That's why we immerse it in a water column and change its length. Length means length of air column. Changing the length of the pipe means changing the length of the air column, because the air column is vibrating inside. So we do like that. But here the experiment is different. We are changing the frequency. We are rich enough, we have plenty of tuning forks, we will change the frequency of the tuning fork. Okay, we have tried it up to 50 Hz. Maximum sound we get now. 51 less, 52 less. Sir, 60 Hz, no sound. Try it with 61 Hz, no sound. 70 Hz, no sound. 80 Hz, sir, weak sound is Hz, sir. 80 Hz. 81, 82, 83, sound is increasing, sir. 95 Hz, very good sound, sir. 100 Hz, maximum sound. That is the second higher frequency. That is the first overtone, second harmonic. So how will be the situation in that case? If it is open pipe and if you want to have the next higher frequency, antinode condition should not be left. This should be antinode and this should be antinode. Antinode, antinode. So lambda by 4, lambda by 4, lambda by 4, lambda by 4. 1, 2, 3, 4 lambda by 4. 4 lambda by 4 is the length of the pipe now. So if L is equal to lambda, then 4 gets cancelled. So what is the velocity or frequency of vibration? Next higher frequency. The next higher frequency of the tuning fork for which the same pipe gives maximum sound. That is next F2 is equal to V by lambda. That is V by L. So shall I write it as 2V by 2L, which is twice the fundamental. V by 2L is the first one. And next one is 2V by 2L, twice the fundamental. You get a frequency which is you get a sound, maximum sound for a frequency which is 100 Hz. For 100 Hz also it gives the maximum sound. This is called second harmonic and this is called first overtone. Got it now? So V by 2L and next one is 2V by 2L. Now you can guess next one is 3V by 2L. If you try for 101 Hz, sound becomes less, intensity of sound will be less. 102 sound less, 103 sound less. 150 Hz again sound will be highest, 3 times the fundamental. So in an open pipe, fundamental frequency is given by V by 2L, where L is the length of the pipe. And next higher frequency is 2V by 2L, 3V by 2L. So for an open pipe, you can write it like this. I'll write it here, open pipe. I'll rub it later when I start the problems. You must remember this one. For an open pipe, fundamental frequency is V by 2L, This is fundamental or first harmonic, right? Because it is 1 times F1. What is F2? It is V by 2V by 2L. That is, this is second harmonic or first overtone, correct? Then F3 is 3V by 2L. It is a third harmonic because it is 3 times the fundamental, and this is second overtone. Next higher, first higher, second higher. Overtone is any higher frequency. Overtone is any higher frequency. But if it is exact multiple of fundamental, we will call it as such overtone. Such harmonic. Second harmonic, third harmonic, 3 times the fundamental. Now in general you can write frequency of vibration is NV by 2L, where N stands for 1, 2, 3, 4, etc. All the harmonics are present in the closed open pipe. In an open pipe, if it vibrates for the fundamental frequency of, then it gives the best sound for 2F, 3F, 4F, 5F, all multiples. What about a closed pipe? Take a closed pipe now. Closed pipe is one which is closed at one end and open at the other end. Now if you take such a pipe, take again the same experiment. Sir, how to make a pipe closed, sir, and change the length? That is the best example. Put the pipe in a water column and change the length of the air column. As you put it inside the water column more and more, the height of the air column goes on changing. That changes the length of the pipe. Here the length of the pipe means it is not the external length, it is the length in which contains air. Okay. You will take a pipe of length L and try it with different frequencies. Sir, 1 Hertz, no sound, sir. 2 Hertz, no sound. 20 Hertz, little sound, sir. 30, little more. 45, very good sound, sir. 50 Hertz, highest sound, sir. Maximum sound. 51, less. 52, less. So 50 Hertz, you get maximum sound. This is only example I am giving. Don't stick on 50 Hertz always. So just to make it understand within a limited time. So for 50 Hertz, we get maximum sound. That is the fundamental. In the fundamental mode, how will be the stationary waves? This is the place where no vibration can occur, because longitudinal waves, the particles don't vibrate here. It is closed end because we have water afterwards, or if it is closed pipe. So this is must be a node, and here should be an antinode. This is the fundamental mode of vibration. Now what is this length? Length of the pipe is lambda by 4. So length of the pipe is lambda by 4. That implies lambda is equal to 4L. So what is the fundamental frequency of vibration? F1. F is equal to V by lambda, V by 4L. So that implies F1 is equal to V by 4L. This is called fundamental frequency. Now start with 51 Hertz, 52 Hertz, 60 Hertz, 70 Hertz, 80 Hertz, 100 Hertz, no sound. This is the specialty of closed pipe. In 100 Hertz also you don't get any sound. That means, don't we get maximum sound? Doesn't it resonate at 100 Hertz also, sir? See, another thing I have not given you the idea. Why does this? Why do these open pipe and wires give maximum amplitude and maximum sound, maximum intensity at that particular frequency? That is their natural frequency. An air column will have a natural frequency of vibration. If you disturb it, it will vibrate with certain frequency, right? If you disturb the water in a tank, it will vibrate with certain frequency. If you disturb the water in a mug, simply vibrate it, it will vibrate with different frequency. If you disturb a simple pendulum, it will vibrate with certain frequency. If you disturb a small ear, that ring, just simply vibrate it, it will vibrate with different frequency. Naturally, they will have different frequencies. Similarly, an air column in a pipe will have a different, its own natural frequency. When the forced frequency and natural frequency are same, they vibrate with maximum amplitude. That is what is needed now. Right? So we are searching for a tuning fork whose frequency matches with the frequency of the air column. 100 Hertz, no vibration. It vibrated with maximum amplitude at 50 Hertz. Now try for 101, 110, 120. Surprisingly, you will find that it again gives maximum sound for 150 Hertz, 3 times the fundamental. It gives maximum sound for 150, not for 100. From 50 directly to 150, 3 times. Why it is so? In the next mode of vibration, it should vibrate with an antinode here, node here. How will you write the situation? It should be like this: a node, an antinode, node, and an antinode node. It should be a node here, it should be an antinode here. See, in a string, if you observe it like this, this is the form of stationary wave, right? If you start from an antinode, where do you get the next node? Here, right? This is the situation. Next node here, right? You should have a situation like this. Am I right? Then lambda by 4 from here to here. Lambda by 4, lambda by 4. 3 lambda by 4 is the length of the pipe. So this is the length of the pipe. Length of the pipe is 3 lambda by 4. What does it imply? Lambda is equal to 4L by 3, right? So what is the velocity of sound here? Frequency of sound, F equal to V by lambda, V by 4L by 3, 3V by 4L. Did you get that? Where is it? 3 times the fundamental. And that's why it is a third harmonic, no second harmonic. If you give the 2 times the fundamental frequency, that doesn't show resonance. Resonance is the condition where the frequency of vibration and natural frequency of vibration of the air column and applied frequency must be same. Only 3 times you get, 2 times not found. That means closed pipe vibrates in odd harmonics. What may be the next situation? It is 5 times the fundamental. That closed pipe may vibrate for say 150 Hertz. That is 3 times fundamental. Next 5 times, 250 Hertz. It won't vibrate for 200 Hertz. This is how it happens, and that is why you see a open pipe can vibrate in many frequencies, but closed pipe can vibrate only in odd multiples of fundamental. Here all multiples of fundamental. That's why sound produced by an open pipe will be pleasant to hear. So, because it vibrates with more harmonics. That's why we say quality of sound is better in an open pipe, because it can vibrate in many harmonics, all harmonics. This closed pipe, sound produced by a closed pipe is lesser in quality because it can vibrate in less harmonics. That's why all the instruments, musical instruments, are open pipes, because the quality of sound is better. So if you just finish it here. For a closed pipe, how can you write? In an closed pipe, fundamental frequency is V by 4L, and this is called fundamental, or you can call it as first harmonic because it is 1 times the fundamental, and the next higher vibration is 3V by 4L, and this is the third harmonic and first overtone. Any higher is called the first overtone, second overtone. There is no problem in numbering the overtone. The first higher frequency itself is first overtone, but multiple harmonics should be exact multiple. It should be 3, that's why third. So what is the third one? Third frequency. It is third, second overtone, second higher, and it is 5 times the fundamental. It is 5th harmonic. And if you want to write in general, V by 4L into N plus half or N minus half. See this one. See the situation. 1, 3, 5, 7 you should get, right? Odd multiples. If it is N plus half, N starts from 0. 0 or V by 2L I have to write. Yeah, we have to write V by 2L into N plus half. V by 2L into N plus half. N 0, 1, 2, 3. What happens? If you put N equal to 0, V by 4L, we get it. N equal to 1, 1 plus half, 1 and a half, 3 by 2, 3V by 4L, so we get it. But if you want to put N equal to 1, 2, 3, etc., you have to write N minus half. If you start from N equal to 1, 2, 3, etc., then you put this as N minus half. What happens? V by 2L into N minus half. N equal to 1, 1 minus half, V by 4L. N equal to 2, 2 minus half, 1 and a half, 3 by 2, 3V by 4L. You will get this. So don't confuse with these formulas. So better you remember this series than no question of forgetting this one. So that is the thing. And you will need to apply this type of vibration in the case of vibration in a quartz crystal, vibration in a rod. Suppose a rod, I will take a rod, I have a pen here usually, yeah. I take a rod, clamp it at the middle. You can see this because my shirt color and pen color has been unique. So you take a rod, clamp it at the middle, vibrate this continuously. By some means, by taking an electromagnet or whatever it is, vibrate it. How will be the fundamental mode of vibration? If you take a rod, fix it in the middle and vibrate it, these two ends are free, they should be antinode and they should be, the ends should be node, antinode, sorry, here it should be a node, these should be antinodes. And the length of the rod must be lambda by 4 plus lambda by 4, lambda by 2. 1/4, half. This is what you have to do. Suppose take a quartz crystal, right, and take two metal plates like this and another metal plate here, apply a battery to the metal plate. When you take two metal plates, apply a battery and let this battery be of AC, okay, and keep the quartz crystal in between. When a potential difference voltage is applied between the two ends of quartz crystal, the other two ends will expand like this. And when the potential difference is decreased, they will contract. So there will be a contraction and expansion on the other two sides. They will vibrate. With what frequency? Then stationary waves will be developed inside when it vibrates. Of course, there is more theory involved in this, but I will take only that part which is needed for my stationary waves. Now, how the stationary waves are produced? In this end. It is very simple. See, these two ends are free. So waveform should be like this. Don't you agree that? The other two ends are vibrating with free open ends and a node should be formed at the center. So again the length should be lambda by 2 because lambda by 4 plus lambda by 4. It is lambda by 2. So you can do that here also. Okay. So shall we move on to the problems? I think I have explained to the maximum. Do you have time to? Yeah, we have time. We can go for few problems. 1 or 2. Yes. If at all I have left anything, we will see that later. Yes. I'll switch it on again. Yes. Problem number some 41 or 42, something like this. Stationary wave. Yeah, we have it here. I can see the laptop. A massless rod BD is suspended by two identical. Yes, I will draw this. So there is a rod. It is suspended by two identical wires. So these wires are in tension now, right? So there is a tension here, there is a tension here. Where is the mass? Mass is somewhere here. It is not in the middle. If it was in middle, I could have divided the tension into two parts. T by 2, T by 2, mg by 2, mg by 2. But it is not in the middle, mg. It is at a distance x from one end, x. So what is the length of the rod? L. Then this is L minus x. That is my addition. It is not in the diagram. So a massless rod BD, okay, you can because this doesn't contribute to the mass, only this mass. Massless rod BD is suspended by two identical masses AB and CD. AB and CD equal lengths. Okay, lengths are equal. A block of mass m is suspended from point P. Okay, this is P. Such that BP is equal to x if the fundamental frequency of the left wire is twice the fundamental frequency of the right wire. So if you pluck it and leave it, they will vibrate. They don't vibrate with the same frequency. Why, sir? Very simple. I will open the door. Light is, camera showing less light? Yeah. Yeah, I will, this wires will not vibrate with the same frequency. Reason is different. Reason is this one. They don't have same tension. Tension here and tension here are different because this is not in the middle. So that tension decides what is the frequency. And if the frequency of the left wire is twice the frequency of the right wire, we decide this one. This is 2f. Then what is their question now? We have understood all the details. Is twice the fundamental frequency of the right wire. Then the value of x is, what is x? Now frequency of a stretched wire 1 by 2L or n by 2L, anything, root of T by mu. wires are identical, lengths are same, no competition, and tension is different, mu is same, identical wires. So shall I take F is directly proportional to square root of tension. Now how to decide tension? Now here tension, this tension, addition must give mg. That is one equation, simply you can write. These two tensions must be equal to mg. Total should be mg. Upward forces must be equal to downward forces, because the rod is neither moving downwards nor moving upwards. Net force acting on the rod is 0 and rod is not rotating. Net torque acting on the rod must be 0. What do you mean by that? This tension, you apply the law of moments, right? Rotational torque. The rotational torque is 0. So this is trying to pull it up by turning it like this. This is trying to pull it like this, right? Turning it like this. The net torque should be 0. That means T1 into its moment, force into perpendicular distance, moment of force, torque. Torque is moment of force. Moment means perpendicular distance. T1 into x and must be equal to balanced by T2 into, because there is no rotational motion, L minus x. So you have two equations from where you can calculate what is the value of x. T1 into x equal to T2 into L minus x. What you will get it from here? You have to put x equal to L by something, right? Okay. T1 into x. What else you have? You can use this one also, right? You have a relation here which says frequency is directly proportional to root of tension. This 2f by this f must be equal to, this condition is very much needed. This 2f by f is equal to root of T1 by T2. So here you get a very important data. Square this. 4 is equal to T1 by T2. T1 is equal to 4T2. Yeah, that is very, very important. You can, here you will get one more, right? That is T1 plus T2 is equal to mg. Yeah, here you get this one. Substitute this one here. What you will get? T1 plus T2 is mg. T1 is 4T2. 4T2 plus T2 is equal to mg. 5T2 is equal to mg. What is T2? T2 is equal to mg by 5. I am using all the possible ways, mg by 5. Here you can write T2 is equal to mg by 5. T1 is equal to 4 mg by 5. Or here itself I can write what is T1 and T2. T1 is equal to 4T2. Whether this is needed, whatever I have written now, whether this is needed, I think it is not needed, isn't it? This is needed. Here we get T1 is equal to 4T2. Now substitute it here. T1. Yeah, that is not needed. This part is not needed. This is enough. T1, shall I write it as 4T2 into x is equal to T2 into L minus x. T2 gets cancelled because our answer should be x and L. X should be something. We have got it here, right? 4x is equal to L minus x. Shall I write it here? 4x is equal to L minus x. Am I right? So this formula and this formula are enough. So one is applying torque, another is frequency relation. 4 into x is equal to L minus x. 5x is equal to L. X is equal to L by 5. Yeah, that is the answer. Yeah. So you have to bring so many things from mechanics. Torque, and another one is frequency of vibration. Option A. We will stop it and we will continue it in the next video. It's already getting time. Okay, I'll come back and I'll finish it. There are still some 20 questions. We have to finish it. Thank you for watching.